Hi, I'm Adam Hand with the University of Nevada, Reno, and I'm going to present the Asphalt Materials Quality Assurance Practices topic, and I'm glad to have the opportunity to do that today. And this is a precursor to the webinar that will be held on September 9th that will be narrated by Tim Aschenbrenner. This material was developed as part of the FHWA cooperative agreement titled Development and Deployment of Innovative Asphalt Pavement Materials. And the University of Nevada, Reno is the prime contractor, and our partners are Applied Research Associates and Paragon Technical Services. We have to read the disclaimer, and this material is disseminated under the sponsorship of the U.S. Department of Transportation in the interest of information exchange under Cooperative Agreement Number 693 JJ 318-50010. The U.S. government assumes no liability for the use of this information. Now, in terms of a background, this presentation is really based on a tech brief. The link to the tech brief is on the page there, and it was written by Chuck Hughes, myself, and Tim Aschenbrenner. And why does it matter? Why did we put this tech brief together? Well, because it's important to agencies, contractors, and taxpayers. Quality assurance is defined as all those planned and systematic actions necessary to provide confidence that a product or facility will perform satisfactorily in service. Well, and everybody has again a stake in that. Agencies, it's important to agencies because they want to make sure they get what they pay for. It's important to contractors because they want to have a level playing field when they go bid and build work. And it's important to taxpayers because they want to make sure that the agencies have been good stewards of their taxpayer dollars. Now, when we implement a quality assurance program, or when an entity does, responsibilities are assigned to different parties. Okay? And we will sometimes end up with some different risk in that situation. Now, this is the 6 core elements of a quality assurance program. And the 2 key elements are agency acceptance and contractor quality control. Now, the other 4 items, technician qualification, lab qualification, as well as independent assurance and dispute resolution provisions, are there to really help ensure the accuracy of the agency acceptance and contractor quality control information that will be used is in the acceptance decision made by the agency. AASHTO R10 has the definition of an acceptance plan, and it's defined as the agreed upon process for evaluating the acceptability of a lot of material that includes lot size, sample size, which would be number of samples, quality measure that's used or measures, acceptance limits, evaluation of risks, and pay adjustment provisions. Now, I said that different responsibilities were assigned to different parties, and that's because different folks do different testing, right? The agencies doing acceptance and the contractors doing quality control. Now, risks, the acceptance plan inherently has risk built into it, and an agency needs to evaluate all those things listed on the slide when developing its acceptance plan, so that the risk is balanced between the contractor and the agency. Now, the risks that, from a statistical perspective, that exists are what we call buyer and seller risks, or beta and alpha risks. Buyer risk is the risk that the agency, the DOT, is going to accept material that they shouldn't be accepting. And seller risk is risk that the contractor will supply material or provide a product that meets the requirements, but does not get paid for because of the inherent risk in the specification. Now, there's also engineering risks, and those risks are really associated with performance, right? The behavior of the materials and the performance of the mix. Now, you're going to see a couple of themes in this presentation. One is lab mixed material different from plant produced material, and you know that can occur. We know it occurs, and it can be unintentional, and it actually can be intentional. And then for today's mixtures, which are you know, you think about volumetrics, go back to Bruce Marshall in the 40s and 50s, and then super pave in the early 90s. So for today's mixtures that are more complicated, the mixes designed back then, are volumetrics alone adequate? And you know, we see that today the industry is looking for simple, quick performance tests that can be used in place of volumetrics in a balanced mix design procedure, or along with volumetrics in a balanced mix design procedure, to make sure that the agency is getting what it wants, the taxpayers' dollars are being well spent, and again that the contractors being fairly treated in the process. I'm going to use a bunch of abbreviations in the presentation today, or you're going to see them on the screen. Now, they're listed here. I'm not going to go through all of these. They're obviously going to be familiar to those of you that are particularly mixed designers, but those of you that work in the industry. Now, there are different times when potential quality assurance risks occur. Some examples include during the mix design process, during verification or sort of startup, as well as during acceptance. Now, the material that's used in mix design is lab mix. At verification, you're using plant mix. And in acceptance, you're using plant mix. Verification is that opportunity, though, either prior to producing mix, if it's done in the lab, or which I think is most important on startup, maybe you call it a startup evaluation or a test strip, where you really get to get the initial look at the plant produced mix, and you can compare that with the laboratory mix to see if there are differences, and if there are differences, dig into why they exist and what can be done to resolve them. Some examples of risks are listed on the slide. There are 7 examples, starting with ignition furnace, asphalt correction factor, and ending with recycled materials. And they're occurring at different times. The first 3 are during the mix design process, and then 1, which is mix adjustments, is in the verification process, and then there are 3 associated with the acceptance process. Now, this isn't an all-inclusive list. It's just an example of some commonly identified risks. When it comes to ignition furnace correction factors, the ignition furnace is obviously used to measure asphalt binder content, and the furnaces require a correction factor that is unique to each furnace and mixture. With the correction factor, what is done is mixes samples are made at a known asphalt content and gradation. Okay, and then those are tested in the ignition furnace, and the difference in the known and the observed asphalt content and gradation can be corrected also, are determined, and then you've got your correction factor or factors if you're going to use gradation correction factors also. But it's important that the agency do ignition furnace correction factor testing, as well as the contractor or the engineering firm working for the contractor. So some risk mitigation strategies associated with ignition furnace correction factors are to only allow the DOT to prepare its own correction factor test samples per T308, which again is a private voluntary standard, for each mixture and each unique ignition furnace, conduct unique correction factor determinations. Okay? In other words, something that I've heard done many times is a sharing of correction factors between multiple ignition furnaces that are the same brand in the same lab. Even that is not appropriate per the AASHTO standard. And another really powerful mix mitigation strategy is to verify the asphalt content that was measured with the ignition furnace using solvent extraction. This is particularly powerful or important when mixes have RAP in them, particularly high quantities of RAP. Aggregate specific gravities, I'm going to just quickly run through a little bit of a reminder on specific gravities. Specific gravity is just the ratio of the mass of a material to the volume of a material. Now, bulk specific gravity, effective specific gravity, and apparent specific gravity, the mass of the aggregate's the same, right? So the only difference is the volume that's being considered. With the bulk specific gravity, it's the volume of the aggregate in the surface voids. With effective specific gravity, it's the volume that's effective, and there's an effective volume because a portion of the surface voids are filled with asphalt binder. So that effective volume is less than the bulk volume. And then with the apparent specific gravity, only the volume of the aggregate, not the voids, is used. So that leads us to the fact that specific gravities have to stack up appropriately. Because apparent specific gravity has the smallest volume and it's in the denominator, it's going to have the largest specific gravity. And if we go to bulk specific gravity, because it has the largest volume and it's in the denominator, then that has going to have the smallest specific gravity. We can't defy physics, though that's a reality, right? So the effective specific gravity is typically about midway between the bulk and the apparent, and that's because asphalt absorption is typically about 50% of water absorption. It's not exactly, but in that ballpark. And bulk specific gravities if a bulk specific gravity is reported to be greater than an effective specific gravity, then there's negative asphalt absorption. So that means there's a bust in the specific gravities, or theoretical maximum specific gravity test, or RICE, that was used to determine an effective specific gravity. Now, there's a relationship, and the reason we're hitting on specific gravities here is there's a relationship between bulk specific gravity and voids of mineral aggregate, or VMA, which is a very common specification parameter. And so if you have small changes or deviations in your specific gravity, it will lead to changes in VMA. And then if a mix designer is doing their job in a low bit environment and designing close to the minimum VMA criteria, you will actually end up with mixes having lower asphalt content than they should have. And what you see in that table there is that if a bulk specific gravity is reported to be 1/100th higher than the actual bulk specific gravity, VMA will go up by about 0.3%, which would allow for a reduction in the asphalt content of about a little over a tenth. Okay. Now at 200ths, again, your VMA difference is actually over-reported by about 0.6%. So in other words, if you had a half-inch mix and you're designing to 14%, and you were right at the spec limit, you would actually have 13.4% VMA, not 14% VMA, and you'd have an asphalt content that was actually about 0.3 lower than it should be. And then as that difference increases, the difference in VMA, reported VMA, and potential reduction in asphalt. This slide shows some data for a state over time. There's a plot of contractor bulk specific gravity on the y-axis and DOT specific gravity on the x-axis. And that particular state had a allowable tolerance between contractor and agency specific gravities of 200ths, plus or minus 200ths. What this slide shows is that in general, so 76% of the time, the contractor reported specific gravities were greater than the public agency specific gravities. Where there's a lot of data on that figure, So, and if it were normally distributed, which we would expect, then there should be about 50% on each side of that line of equality. So it's showing, it suggests there's a bias towards higher contractor-specific gravities. And that's a sort of a risk associated with using tolerance. So what are some risk mitigation strategies for aggregate-specific gravities? One is to routinely measure them and compare them with mixed design values. Some things that state DOTs do is, for individual mixed designs, go ahead and measure the aggregate specific gravity, especially if you've got variable aggregates in the area. Some agencies will use what they call bench values. So what they'll do is they'll go in and you get a big limestone quarries in the Midwest, for example. The quarry operator will go in, form a bench, and then the samples will be taken, and sort of book values for that bench will be established and used by both the DOT and the contractor. And the DOT would make those measurements. Other techniques observed are at fixed frequencies. It might be on a tonnage or a tonnage of production, or on a time frequency, for example, every 6 months. And that would depend on variability of the source again, and the agency would establish that. And then verifying mix design, bulk specific gravities during project startup evaluation. So you had a bulk and mix design. You go to production. If you pull samples, cold feeds, for example, and run gravities, are they still in the same ballpark? The other thing that can be done is reporting of all those properties that are listed: apparent bulk, effective specific gravities, asphalt absorption, and absorbed asphalt in the mixed design submittals, and verifying then when the submittals are reviewed that the gravities stack up appropriately, the amount of absorption is in the right ballpark. And then finally, analyzing differences in DOT and contractor specific gravities, and then sharing those with industries as a function of time. That's what that previous plot was. You get, I don't know, pavement association meetings annually. You could do that type of thing. So in summary, we want to use actual values, not tolerances, for bulk specific gravities. We want agencies tests. Using agency tests is important. Again, they may be specific values for each mix design, or some of these different types of book values that I talked about, for again, benches are based on tonnage or time frequencies. Now we've looked at specific gravity and VMA, and with years ago, when we started using small quantities of RAP, we would use effective specific gravity for our RAP specific gravity rather than the bulk specific gravity. The reason for that is you had to go ahead and extract, use solvent extractions to get the aggregates and then run the bulk specific gravities. Now we have ignition furnaces, and both of those techniques, though, take time and effort, right? Where a very simple, quick technique would be to measure the GMM, or theoretical maximum specific gravity, of a mix at a given asphalt content, known asphalt content, and then, or measured asphalt content, either one, and then calculate the effective specific gravity. Much quicker, much easier. Now, again, when we were using 10% RAP, that wasn't a big deal, but we're seeing 25 to 35%. Some states are allowing up to even 65% RAP in mixes. And this slide shows an example from some data I found handy, where by using 25% RAP and the effective specific gravity, the VMA that's reported is actually 0.3% higher than the actual VMA, if the bulk specific gravity of the RAP had actually been measured. Okay. Now that's going to be mix dependent. This is an example with aggregate specific gravities that are a little higher than the example I just showed. And in this example, we got 20% RAP, and the water absorption is 1%. And using the GSE was similar to having a specific gravity, bulk specific gravity that was a little over 200s higher on the composite mix. VMA that was about 0.6% artificially reported a high, and allowing the asphalt content to be dropped by about 0.3%. So those are just a couple of examples of why it matters. So in terms of risk mitigation strategies, don't use GSEs for RAP. Use bulk specific gravities. Don't allow the use of estimates of G sub SBs. Again, get the real GSBs and use them. And then use GSBs for all the materials, just the virgin aggregates as well as the RAP, and then monitor and verify GSBs during production. The next category or time that we said risks occurred was in verification. That's in making mix adjustments during startup. NCHRP report 818, which was developed by the folks at LSU, entitled Comparing the Volumetric and Mechanical Properties of Laboratory and Field Specimens of Asphalt Concrete. It summarizes work where I think it was 7 states that they got mixes from around the country, and they prepared what they call design or lab mixed, lab compacted, production, which was plant mixed, lab compacted, and construction or plant mixed, field compacted specimens. And they measured the volumetric properties listed on the slide there, as well as rutting, dynamic modulus, and indirect tension dynamic modulus. And they varied baghouse returns, specimen fabrication time, aggregates had varying absorption levels, hardness levels, and stockpile moisture levels. And they looked at the influence of those factors on those volumetrics and mechanical properties. They found that air voids were impacted by stockpile moisture. Asphalt binder content was impacted by baghouse fines, and aggregate gradation had an impact, and that was basically if the return of the baghouse fines led to differences in amount of material past the number 200 sieve, and that impacted those properties. So in this slide here is a summary from the report, and they came up with, for the different properties, okay, the volumetric properties and gravities, the single operator confidence limit as well as maximum allowable range. And the point here is differences occur, okay, and it's good to understand what those differences might be and go ahead and make adjustments to either minimize or eliminate them. So as a rule of thumb, when it comes to binder content, about 1/10% change in binder content will lead to about 1/4% change in air voids. So you increase your asphalt content 1/10%, your voids go down about 1/4%, or vice versa. You reduce your asphalt content, your voids will go up. When it comes to aggregate adjustments, a 1% change in P200s can lead to anywhere from about 0.3 to a 1% change in VMA, and it depends on the gradation type, and I'll share some more examples on that in a minute. When it comes to coarse graded mixes, if you reduce the amount of material passing the number 8 sieve, will increase your VMA, and conversely for the fine graded mixes. It's good to make gradation adjustments prior to making binder adjustments with the goal of trying to keep binder in the mixes. So this is a summary of some work that was done by CDOT, and what you have is 3 different mix types here. So you got fine gradation, straight gradation, which you might think of as being sort of parallel to the maximum density line, and then coarse gradations. And then in the rows, you see the influence of P200s and crushed products. And so, for example, in the second row, if you look at P200s going from 8% to 3%, in a fine graded mix, that led to about over a 1.5% increase in VMA, where in a coarse graded mix, it only led to about 0.3% increase. Now, if we go to the bottom of the table and we looked at the amount of crushed material that was used, when you go from 80 to 100% in a fine graded mix, that only led to about 0.3% change in VMA. In a coarse graded mix, it led to about a 1% change in VMA. And the point here is that these changes are going to be unique to each individual or unique gradation that's used on a project. You really need to keep that in mind. And again, with the goal of keeping the asphalt binder in the mix. So what do we have for mitigation strategies associated with mix adjustments? One really important thing is in standard specifications or construction manuals indicate how to adjust differences in mix design and plant produced mixtures. A lot of specs are void of that. Only allow gradation adjustments before allowing asphalt binder content adjustments. In other words, try to get that difference between the volumetrics from lab to field mitigated by making gradation adjustments. Okay, and this may include adjusting the amount of baghouse fines that are returned, and it may even require that some be wasted. Include VMA and dust to asphalt ratio, or dust proportion acceptance criteria, our plant produced mix that are equal to the minimum values in the AASHTO M323, and only allow baghouse fines to be returned to the drum mixing plant or to the batcher. Well, never mind, it's on a continuous mix plant, to the drum if they're interlocked and they're accurately metered. So in other words, you don't want a screw feeding that's running at a constant vein feeder, running at a constant speed, returning fines to the drum when the production rate in the drum is going up and down. Because as the TPH, the tons per hour running through the drum, changes, if you have a constant feed of baghouse fines, then their 200s are going up and down. So again, you need one, they need to be interlocked, and two, they need to be accurately metered. Okay, this slide has got some sort of what ifs. Again, it's a rule of thumb or ballpark kind of thing that you can look for. And in this slide here, you've got relationships on the right. So when GMM goes up by 100, air voids go up by 0.4%. When GMB goes up by 100, air voids go down by 0.4%. When GMB again goes up by 100, VMA changes or goes down by 0.4%, and that makes absolute sense. It should. And when GSB changes by a hundred of 1%, again we get a related VMA change. So this is a sort of an absorption check, and really what it is, it's sort of a reality check that we can't defy physics, right? We know apparent, effective, and bulk specific gravities have to stack up the way they're shown on the slide. So if you review a mix design and you've got apparent and bulk specific gravities that are equal, you've got no absorption. Something's clearly wrong. If your effective specific gravity is equal to your bulk specific gravity, you have no asphalt absorption. Again, something is wrong. And if your effective specific gravity were equal to your apparent specific gravity, your asphalt absorption would be equal to your water absorption. Again, something's wrong, right? There's a problem. So your GSE is typically about midway between your bulk and apparent specific gravities, and that's because your asphalt absorption is typically about 50% of water absorption. So for a given mix, the relationship between apparent, effective, and bulk specific gravity shouldn't change. Now, again, there's small changes in gradation and so forth in production, or variability associated with testing, but you shouldn't see big changes in those properties. You might see some changes in the effective specific gravity due to the time of the mixing temperature, how hot the mix is, the production temperature, the storage time, how long the mix is kept at elevated temperature. If you take an aggregate with high absorption capacity and you leave it in a silo for 24 hours, you'll get a change in your rice from your from if you had taken a sample that shortly after production, and then if there's a change in aggregate products. So you can use control charts to identify trends. This is some data that's provided by CRH America, and what this shows, in the first column you've got tests, and there's over 25 tests there. You've got GSE values that are calculated by taking samples in production, measuring the GMM and the asphalt binder content, and then calculating them. In the third column, you have running averages of the previous 4 tests. The next 2 columns that are titled design values, GSA and GSB, are the values from design. To the right of that, you've got the absorption capacity, which again is a fixed number. Goes back to the previous columns. And then you have, in the second to the last column, you've got percent binder absorbed, and that is about 0.35 to 0.95 or 99. And then finally, the ratio of percent absorbed binder to water absorption. And again, if you go back to that 50% rule, we would be looking for about 50 in that last column. So if you're monitoring this and you get a change in absorbed binder, you need to go back and look at your GSBs. Control charts are really simple, and this is a great tool If you do a control chart, you put your design apparent and bulk gravities on there, and then you plot your effective as a function of time, it's really easy to pick up changes, and when those changes occur, you know you need to go do something about them. This slide shows the relationship between theoretical maximum specific gravity and asphalt content from a mixed design, the solid line, moving from left to right. We know as asphalt content goes up, theoretical maximum specific gravity goes down. So you've got the mixed design values on there, then you've got some field production values. So there's two things you want to look at. One is how close are the field production data to the mixed design? Is there a shift? How large is the shift? And then directionally, are they going the same direction? You can see in this example there's a pretty good shift, although directionally they're going in about the right direction. Now, this is actually data from a project, and what you see here is you've got the relationship that's irrational. In other words, as the asphalt content goes up, the theoretical maximum specific gravity goes up. That's physically not possible because the specific gravity of the binder is less than the specific gravity of the aggregates. And on this particular project, you see a lot of data there. The pay factor on this job was 105% for the mix, or 1.05 for the mix. And these relationships weren't monitored. Again, simple tool, measure them and use them in production. So what do we have for mitigation strategies? Verify your G sub B's during startup, mixed design and startup evaluation. Monitor your specific gravities and absorptions during production. Make sure that they're rational, the trends are in the right direction. The absorption is no more than about 50% or is in the ballpark of about 50% water absorption. And an easy way to do that is with control charts. And then have specification provisions that direct what should be done when these differences exist. The last mitigation example I'm going to hit on here is acceptance of this is wrap as an example, but it could be anything, wrap, raz, fillers, fibers, rubber, whatever. And the question's asked, how do you know that you're getting the specified quantity? Well, some risk mitigation strategies are one, to make sure that your plant's calibrated and verified on a regular frequency, and that the calibrations are documented, the verifications are documented, and they're witnessed by a plant inspector. Having RAP and RAS production and stockpile QC programs, which will flag inconsistencies that can be addressed while those materials are being produced, rather than after the mix is coming out of the plant. Having specification items for reconciliation of plant control data logger reports and loadout tickets, as well as JMF targets and plant stockpile inventory, and even asphalt binder inventory at an individual product level, okay, or individual project level. This is really easy on portable jobs. It's a little more challenging in town, but it's a good process to use. And then surveying dedicated piles of RAP. That's not a rational thing to do with RAS because the piles are so much smaller. And then having inspectors at asphalt plants. This is an example of a recordation. This is a basic data logger output. And basically you're looking at, are the percentages that are on there coming out of the plant report consistent with the JMF from the mix design? Is the asphalt content set point correct? Is the contribution from the RAP correct? Is a moisture correction in there, and is it correcting appropriately? Another one is with recycled materials having appropriate bins. Bins are are specifically designed for feeding recycled materials, in particular RAS. RAP, you can use cold feed bins. You just have to be really careful. Make sure you got scalping screens on them. The steeper the sidewalls on the bins, the better. And if bins have air cannons and vibrators on them, again, they'll prevent clumping of material that will then slip off and lead to slugs in the feed. Having a reverse waste system is fantastic. This is an example. You can see with the dotted circle, this bin is actually sitting on strain gauges and actually being measured. So the actual weight is constantly being measured. So it's a reverse waste system. Then having a uniform feed, and there are not only getting it uniformly coming out of the bin but again, keeping it uniform as it goes into the plant. And one of the things with RAS is it's, especially in warm climates, it's good to empty your bins at night. So in summary, we have engineering statistical risks, and they have potential costs associated with them. The risks have changed with transitions from method to QA specifications. Risks exist because specifications lack detail. Lack of detail leads to different interpretation of specification intent. An example, one that's really common, is retesting. Do your specs address retesting, whether it can or can't be done? And if it can be done, what the process is and how the data is used. And it's the DOT's responsibility to review their policy, design standards, test methods, and practices and specification for acceptance risk. And make changes based on the risks that are identified and communicate and train on those risks. Now, I personally believe that the contracting industry has a responsibility there, and that is to help the DOT with the review of their specifications to identify risks and opportunities for again, making sure that everybody's getting what they want, the agency, the contractor, and the taxpayers. Now, in wrapping up, I'm going to share an example from Maine DOT where they had, in 1 year, they'd experienced an estimated 20% loss of pavement service life due to raveling at a cost of about $15 million, estimated to be about $15 million. They went through their specifications and they identified 7 potential causes. One was higher production P200, their specifications and data, higher production 200s without a production dust to asphalt criteria, no aggregate durability test, insufficient thickness to nominal maximum aggregate criteria, not verifying GSBs led to inaccurate volumetric properties, higher than desirable permeability from multiple causes, and then no moisture susceptibility test. So what they did to improve their test, the items they selected to improve their test methods, specs, and practices to reduce these risks were to improve the weighing of pay factors for the 200 sieve and P200s from design to construction criteria, so having some tighter criteria on that, and then implementing a field-produced dust-asphalt ratio criteria, improving the acceptance and validation process for bulk-specific gravities, and then implementing a wheel track test for moisture susceptibility and rutting, and then implementing an aggregate test to improve aggregate durability, and then establishing guidelines for thin overlays that included thickness to nominal maximum aggregate size and gradation type. It's worth noting that there are 3 AASHTO standards that are really good tools when you want to look at quality assurance risk, and they're listed on the screen here. With that, I will thank you for watching today, and hope that you will watch the actual webinar on the 9th. Thank you.